Hello friends, this is lecture number 6 of EMT electromagnetic theory, and today we are going to discuss about electromagnetic wave in free space. Okay, so this is our topic of discussion today, and this is lecture number 6. I have provided the links of previous lectures in the description box. If you haven't watched yet, then you may go through. Okay, and before we start, please subscribe the channel, hit the bell icon so that you get notified when new video will be uploaded, and please support me and help me to grow my channel, inspire me to create new contents for you. Okay, so now if you want to follow me on Insta, this is my Insta ID, Lakhyajit 123. Okay, so electromagnetic wave in free space. So first, what are the Maxwell equations? Okay, first let me give you the Maxwell equations, and we're gonna obtain the wave equation, electromagnetic wave equation from the Maxwell equations. Okay, so Maxwell equations. What are the Maxwell equations? Del dot E, that's going to be equal to 0. Actually that is equal to rho by epsilon naught, but for free space, this charge density rho is equal to 0. This is charge density. So that's why we can write for free space this Maxwell equation. This is going to be equal to y, right? Since for free space that charge density is equal to 0, right? And next equation is del dot B is equal to 0, where B represents magnetic field, E represents electric field. Hope you know this. So E represents electric field and vector B represents magnetic field, right? And del cross E, that's going to be equal to minus del B by del T, right? So this is first equation. Suppose this is second equation. Let me use another color. Yeah, this is the first equation, this is the second equation, and this is the third equation. And next, the last one is del cross B. That is equal to del cross B is equal to mu naught J plus epsilon naught del E by del T, right? Okay, but for free space, J is gonna be equal to 0, so we can write this equation mu naught epsilon naught del E by del T, because for free space the current density, current density J, that's gonna be equal to 0. So that is why, so this is equation number 3, right? Not 3, this is 4. This is equation number 4. So that's why del cross B for free space is gonna be equal to this, right? So hope you have understood this. So now taking curl of equation number 3. Now let us take the curl of equation number 3. Taking curl of equation number 3. So if we take curl of equation number 3, this is the equation number 3. Let me copy the equation. Yes, so let me paste here. So if we take curl of this equation, then what we can do, so here you see we can write this way. So we're going to take curl on this side as well as on the other side, and here it can be written this way. The curl can be written inside curl of B, right? So I have taken curl on both sides. Then this implies, and if you have the clear concept of vectors, then this can be written this way, that del dot del here del, then del dot E, right? Del of del dot E, minus, sorry, not minus, equal to, just wait, minus del square E vector is equal to minus del T of we can replace this curl B by this, whereas curl B by this equation number 4. We can use here equation number 4. If you use this result here, then it's gonna be equal to mu naught epsilon naught del E by del T. That's what we're gonna have, right? So let me copy this and let me go to the new slide. Okay, let me copy this and let me go to new slide. So here you can write one more thing. So using equation number 4, just wait, that's how we can do. So now let me go to the next slide. So this is the result we have got. Okay, so now what we can do, here you see, now you see, just a second, let me go back to the previous slide. Here you see, in this case, del dot E from Maxwell's equation number 1, del dot E, that is equal to 0 here, because in free space the charge density is 0, right? So now let me go to the next slide. So from equation number 1 we can get this is equal to 0. So that's why this equation implies minus this is equal to this is going to be equal to minus, so these two can be taken out, mu naught epsilon naught. Then so if you differentiate it twice, that's going to be second order derivative. So we can write this second order partial derivative of electric field E with respect to T. So let me write it properly, just wait. So this is what we have got. Now you see, so this minus gone. If you bring this down to this side, then what you're gonna have del square E minus mu naught epsilon naught second order partial derivative of E with respect to T, that's equal to 0, right? That's equal to 0. And this is what, so here you can see, if you observe, this is the differential form of a wave, right? So here this mu naught epsilon naught, that is equal to 1 by v square, and which implies that v is equal to 1 by root over mu naught epsilon naught. And if you put the value of mu naught epsilon naught, and that's approximately equal to 3 into 10 to the power 8 meter per second, that is the speed of light, right? So that's why this equation can be written in this form. Sorry, 1 by c square, right? sorry, is equal to 0. So this is what we're going to have, right? So this is electromagnetic wave in free space, wave equation in free space. So this is for electric field. Similarly, for magnetic field, we can obtain that similar kind of equations. Let me show you how. So let me go to, just wait, let me make a partition here, just wait. Okay, so here you see, let me go to the previous slide. So from this equation number 4, B cross del cross B is equal to mu naught epsilon naught del E by del T, right? So from equation number 4, what we have got, that del cross B is equal to mu naught epsilon naught del E by del T. That's what we're going to have. So again, if you take curl on both sides, curl of B and mu naught epsilon naught del, sorry, yeah, it should be del T only, right? Del T curl of E, right? That's how we can write. So then what we can do here, so again, if we apply the concept of vector here, we're going to get del of del dot B minus del square B. This is just a formula that you have got in vectors, right? So, and here you see this curl of E. Let me go to the previous slide. So curl of E, from equation number 3, what we get, so this is the curl of E, right? So if we use this value here, so here we can use that value, then what we're going to have, we're going to take minus sign outside, then del T, then curl of E, we have got minus del B by del T, but minus sign is taken out already here, right? So that's what we have got. This is from equation number 3. So here you see, this is the equation number 3. Okay, so now again del dot B is 0. Here you see in this slide, so in the equation number 2, here you have got that del dot B is 0, so we can replace this by 0. So that's why this equation becomes minus del square B minus mu naught epsilon naught second order partial derivative of B with respect to T. That's what we're going to have, right? So let me copy this and let me go to a new slide. Let me take a new slide, just wait. So here is the result we have got, right? So now let me go to the previous slide again. Here, so what we have used using equation number, so here we have put 0. So from which equation we have got? From equation number 2, from this equation. So using equation number 2, and yes, so now you see again here minus minus cancels, so this equation becomes del square B minus mu naught epsilon naught second order partial derivative of B with respect to T is equal to 0. That's what we have got, right? So similarly, this can be also written as 1 by c square del second order partial derivative of B with respect to T is equal to 0. So this is the electromagnetic wave equation. equation, right? So what was the last equation we have obtained? Let me go to the previous slide. So here you see this is another equation. Let me copy this one also. So let me put here. Now here you see, so that's why as we have got two equations, this one and this one contains electric field and this contains magnetic field. So the electromagnetic field will be something like this. Electromagnetic equations, wave should be like this. Let me show you. This is the x-axis, suppose this is the y-axis, and this is the z-axis, and suppose the wave is propagating along the x-axis, and if this is the magnetic field, this is the electric field, suppose. Let me draw it properly. This is the electric field propagating in this direction, suppose. Let me write it properly. This is, just wait, this is the x direction, propagating in x direction this way, right? Then the electromagnetic wave, the magnetic field, okay, so that's gonna be in this direction. The wave represented by this equation will be in this way. It's going to be oscillating in this way. Just let me show you. Right, so here this is the wave represented by this equation. This one represents this equation, this wave that you can see in red color now, which is oscillating perpendicular to the x direction in xy plane. This is in xy plane, and whereas the wave represented by this equation containing magnetic field is oscillating in this plane, zx plane. This is zx plane, right? And this zx plane this way, right? So hope you understood this. Okay, so one wave is oscillating this way, another this is vertically up and down, and another is horizontally right and left, right? So hope you have understood this. So that's why if we write the solutions of these equations, so we know the solutions of this kind of equation, or equation of this form of wave, can be written as E vector. The solution of this equation can be written as E vector E naught, that represents amplitude, right? Sine kx minus omega t. So here kx, x, that means the wave is propagating along x-axis, and here you see the electric field is oscillating. This electric field is oscillating in xy plane, and that means it is oscillating in y direction, right? The amplitude, direction of the amplitude is in y direction, like this, vertically, this way. This is the y direction, right? Amplitude, direction of the amplitude is y direction. So let me write the unit vector along the amplitude in y direction. Let me write ay cap, right? And similarly, solution of this equation can be written as vector b. So b naught, that's amplitude of the magnetic field, a magnetic wave, that here you see we're gonna have sine kx omega t, here a z cap. So because this is the magnetic wave is oscillating along z direction, right and left, okay? So that's why we have got z. So hope you have understood. So these are the equations of electromagnetic wave in free space, okay? So hope you have understood, and in the next video we're going to discuss about electromagnetic wave in dielectric mediums. Okay, so thank you for watching. See you in the next video.